Welcome to Semester 6 Statistics at Delhi University. Today we are diving into the fascinating world of multivariate analysis and non-parametric methods, specifically focusing on a concept called sign tests. We will learn exactly how to test hypotheses when our real-world data does not follow a perfect symmetrical bell curve, using a beautifully simple yet incredibly powerful statistical technique. To begin, let us understand what a sign test actually is. Imagine tracking weight loss. Instead of exact pounds, you just ask, did you lose weight? Yes or no. This is a non-parametric method, meaning it does not assume our data follows a strict mathematical shape like a normal distribution. Instead of the mean, it evaluates the median. By throwing away exact numerical values and keeping only the direction of change, the math becomes incredibly robust against extreme outliers. One person gaining 50 pounds will not skew our results if everyone else lost too. Now that we understand the core idea, let us look at how we mathematically assign these signs. We start by calculating the deviation for each data point. The formula is di equals xi minus m0. Here, xi is the actual numerical value of our specific observation. M0 represents the hypothesized median we are testing against. If our data point is greater than the guessed median, the deviation is positive, giving us a plus sign. If it is less, we get a minus sign. Any data point exactly equal to the median gives a 0, which we completely discard because it provides no directional information. This brings us to how we evaluate the total number of positive signs we just defined. Under the null hypothesis, getting a value above the median is just as likely as getting one below it. Therefore, the count of positive signs follows a binomial distribution, exactly like flipping a fair coin multiple times. The probability of observing exactly key positive signs is given by this formula. The symbol n is our total sample size after discarding any zeros. The probability of a positive sign on a single trial is p, which is always exactly 0.5 under the null hypothesis. If our observed number of positive signs has a very low probability, we reject our guessed median. Before we move on, let us see this with a concrete example. A bakery claims their bread loaves have a median weight of 500 grams. A customer weighs 8 loaves. To test the claim, we first subtract the hypothesized median of 500 from each loaf's weight. This gives us our deviations. Notice that one loaf weighed exactly 500 grams, resulting in a difference of 0. We discard this 0, leaving us with 7 valid observations. Counting them up, we have 5 positive signs and 2 negative signs. Continuing with our 7 valid loaves, we want to find the exact probability of getting exactly 5 positive signs if the bakery is genuinely telling the truth. We plug n equals 7, k equals 5, and p equals 0.5 into our binomial formula. We expand the combination notation into its factorial form, which is a mathematical way of counting the different ways to arrange 5 successes among 7 trials. We also simplify the second probability term, combining the exponents since multiplying numbers with the exact same base means we simply add their exponents together. Let us calculate the final probability. We compute the factorials and find there are exactly 21 different ways to arrange these signs. Multiplying this by 0.5 raised to the power of 7 gives us our result. We get approximately 0.164 or 16.4%. This means there is a 16.4% chance of getting exactly 5 heavier loaves just by random luck. Because this probability is relatively high, we do not have strong evidence to call the bakery a liar based on this sample. So we have successfully used the binomial formula for a small sample. But what happens when our sample size gets large, typically greater than 20? Calculating factorials for large numbers becomes incredibly tedious and mathematically heavy. Fortunately, as a binomial distribution grows, its shape smooths out and begins to look exactly like a classic bell curve. Because of this, we can use a normal approximation to solve the problem much faster without losing statistical validity. To use this normal approximation effectively, we calculate a z-score. This standard formula tells us exactly how many standard deviations our specific result is away from what we originally expected. The symbol S is our observed number of positive signs. The expected mean, mu, is simply the total number of trials n multiplied by the probability p. The standard deviation, sigma, measures how much the results naturally spread out around that mean. A higher z-score means our result is highly unusual and incredibly unlikely to happen by random chance, giving us strong evidence against the null hypothesis. Let us apply this z-score formula to a new scenario. Suppose 40 students take a training course. We find that 26 improved, giving a positive sign, and 14 did worse. We want to test if the course had a significant positive effect. First, we calculate the expected mean. 40 students multiplied by a 0.5 probability gives an expected mean of 20. Next, we calculate the standard deviation by taking the square root of n times p times 1 minus p, which gives us approximately 3.162. Now we substitute our calculated values back into the z-score formula. We take our actual observed 26 improvements and subtract the expected 20. We then divide that difference of 6 by our standard deviation of 3.162. This gives a z-score of approximately 1.89. In statistics, a z-score near 2 is generally considered the threshold for significance. Because 1.89 is fairly high, it suggests the training course likely did have a real positive effect, sitting just on the borderline of standard statistical proof. Now that we have used both small and large sample methods, let us discuss how the sign test compares to other statistical tools. Statisticians look at two main things: power and efficiency. Power is the ability of a test to correctly detect a real difference when one actually exists, like a smoke detector going off during a fire. Efficiency measures how much data you need to achieve that power. Because the sign test throws away exact numerical values, it loses some valuable information, which impacts its efficiency. To measure exactly how much information is lost, we use a concept called asymptotic relative efficiency. This formula states that the efficiency of the sign test compared to a standard t-test on perfectly normal data is exactly 2 divided by pi. This equals approximately 0.64 or 64%. In plain English, if a standard t-test requires 64 patients to prove a drug works, the sign test would require 100 patients to provide that exact same level of proof. This brings us to a visual understanding of how the sign test makes decisions. Look at this diagram of a binomial distribution. The tall blue bars in the middle represent the acceptance region. They show that getting roughly equal numbers of positive and negative signs is highly probable if our guessed median is correct. The short red bars at the extreme edges represent the rejection regions. These outcomes are so rare under the null hypothesis that if they occur, we are forced to conclude our guessed median was wrong. We have covered a lot of ground today, so let us review the key takeaways. The sign test is a beautifully simple yet highly robust tool that tests claims about a population's median by converting data into positive and negative signs. It uses the binomial distribution for small samples and a normal approximation for larger ones. While it sacrifices some statistical efficiency compared to parametric tests requiring slightly larger sample sizes, its absolute immunity to extreme outliers makes it an indispensable method in real-world data analysis. Great job following along.